All right, guys. Well, welcome to our fourth webinar, Introduction to DCC. Just a couple of things. I've got a lot of stuff here that we're going to try to get through relatively quickly. Try not to be too overly technical, but still want to give you the information on how DCC operates and how it works. So there will be a lot of stuff going through, some technical stuff. So if you do have any questions, make sure you type them in, and we'll try to address them at the end. If you need clarification on something, we can always go back and revisit a topic. Just really quickly here, my name is George Bogatuk. I'm working with SoundTraxx now over 10 years, and I haven't worked a day since I got here, so it's a good thing. My history, I've been a model railroader since I was 13. I've actually been using DCC for about 25 years or so, and I remember a story that I like to share. Personally, I had bought my DCC system a while back, got home and started reading through the instruction manual and thought, oh my God, what am I getting into? And so I boxed it up and put it away. And at the time I was using a product called Rail Command, which was one of the carrier control proprietary systems. Anyway, I had it for 2 years, and over that time, more and more products, more and more manufacturers were going to DCC ready stuff, and even some decoders were starting to be factory installed. And I thought about it for a minute and went, wait, I've already did the hard part. I already spent the money, so let me just jump in and learn it. And so I did, and opened it up and actually read through it and played with the DCC system that I had bought, and became familiar with it and realized that it was a lot easier than I made it out to be. Now, there are going to be differences in different systems, and we'll kind of talk about that as we get through the class today. But my point of the story is, now I'm working in the industry and I'm helping out and doing clinics and stuff all over the country. And at one point in time, I was a little nervous and apprehensive when I opened up my DCC system. So guys, have the confidence, jump in there with both feet and learn it. And this is going to take you a good step. This class that we're going to do today is going to take you a good step, but don't be afraid to jump in there and learn it. And with that, we're going to start off today with our first poll.
All right, so our first poll is, what is your DCC experience or experience level?
So let's go ahead and get started. First of all, we're going to talk about the digital advantage. One of the biggest things is this is an industry standard protocol. The NMRA actually owns the DCC signal, and where it's standard is the signal that's actually on the rails is what is standardized. And so that way our decoders will work with any NMRA DCC system, and every other decoder can work with those as well, and every system can control our decoder. So it's very standard. And because of that, the different manufacturers are able to build products. There's a wide range of products that are available in the DCC market. We have a wide range of products ourselves with non-sound motor decoders, as well as the sound decoders that you know and love, the Econami, the Tsunami2, and of course the SoundCar. Now, the other thing is it's a more secure investment. And, prior to the NMRA adopting the DCC standard, you had a lot of small cottage industries creating carrier control or some sort of a command control system. And, what would happen is if that company went out of business, or, God forbid, the owner got run over by a bus or something, then all of that is lost because there's nothing else to continue with making that product. And so with the NMRA DCC, if, say, for example, if one of the decoder manufacturers were to go out of business, you don't have to reinvent the wheel and do all of that. You have that secure investment knowing that you'll be able to continue in DCC. A large knowledge base. Now, DCC's been around for quite some time, so you have a lot of people in your area who have been using it and understand how the different systems. So when you pick a system, kind of take that into account, what is used in your general area. And, also the other side of this, I'll say, is the knowledge base. Also kind of get a couple of opinions, because with the advent of the internet, there is always experts who actually don't know what they're talking about posting online forums. So we're always a phone call or an email away. If you have any questions about our product, we're glad to help you. And the last one here is, because the technology works through the rails, it's good with any scale. So Z scale, N scale, all the way up to O scale, G scale, and larger. You can use the same technology. You just have different power requirements, and that's all separate, controlled by the boosters, and we'll get into that in just a minute. Now, when it comes to high degree of functionality, you have a lot of control when it comes to DCC, including speed, lighting effects, and sound decoders and other accessories. Being able to actually control your locomotive a little bit more accurately using decoder, using DCC. And with that, the superior signal. The track is always at full voltage, and so therefore you don't really have to worry about the issue of a weak signal being sent through, provided you're following your proper wiring techniques. The data encoding has a high level of noise immunity. There's not really much interference with other things like radio or other types of microwaves or anything like that. The signal's pretty clean and pretty simple, so it runs through pretty well. And then minimal impact by layout wiring. As long as you follow procedures, your track buses are typically 12 to 14 gauge and your feeders are 16 to 18 gauge. You shouldn't really have an issue. Really shouldn't be using something like 30 or 32 gauge wire for your feeders, because that's where you start running into power issues, because you really want to make sure your track is fully powered. So things like that will help out. It's pretty universal, and so it works really well. Now, when we get into the advantages, it's a lot more fun. With the Power Pack, you had the control panel where you had all your rotary or toggle switches to run track power from one section of track to the other. And now you can actually do more of like with a walk around throttle, where you have the throttle in your hand and walk with your trains. You've got a lot more features. With the old Power Pack, basically you change the voltage on the track and that's about all you have. So hopefully you have some constant lighting circuits or things like that inside your models. But now you get to run you have access to a lot more features. You can even throw turnouts using DCC. This runs your locomotive, not your track. Again, with old block control, every locomotive that was on a section of track would run forward or reverse together. And this gives you the ability to actually run the locomotive. So you get to be more of the engineer rather than just simply adjusting a knob on a box. This leads to more prototypical operation, and this is something that we've built a lot of into the Tsunami2, is prototypical operation using sound and control of the motor, so you can actually do things like set the brakes and charge your train lines and blow your whistle signals and things like that when you're running your train. So it gets you a lot more involved, and it's a lot easier to run multiple trains because they all have their own unique address when they're running, and so therefore you can control 2 or 3 trains at a time with different throttles. So there's a lot of advantages. So with that, we're going to reveal the results of the polls and kind of see where everybody's at. So it looks like we've got quite a few right about in the middle. We've got a few experts, so hopefully this will give you some information and something to learn. And then we've got quite a few beginners. So welcome, guys. So with that, let's get into the nuts and bolts. So when we talk about DCC systems, there's actually 5 basic parts. You have the cab, or what's also known as the throttle. You have the command station. And then you have the power station or the booster. Then a mobile decoder, which is what SoundTraxx manufactures. And then you have the accessory decoders. We're going to take a look in depth of each of those. So first off is the cab. Now this is actually the throttle that you run your train with, and it's nicknamed the cab because typically it's acting as if you're in the cab of the locomotive. So you have full control of that locomotive or that train by sitting in the cab. Now this provides control for speed, direction, and other functions, being able to blow the sound, for example, blow the whistles, ring the bells, things like that. Now there's different types of cabs. They can be tethered, which is wired or plug into the either the command station itself or into a throttle bus that runs around the layout if you have a relatively large walk-around layout. They can also be wireless, and they use some sort of radio protocol or Bluetooth or other Wi-Fi type data transmitting, and so these are becoming more and more popular nowadays, especially with walk-around style layouts. And then, of course, there's also the ones that are built into the command station. This is things like, for example, the Digitrack Zephyr, or I know the Easy DCC from CVP Products has 2 throttles built into the command station that sits on the desktop. So it just depends on what type you're looking for and what your layout needs are. So there's different types. And the best part is any DCC system can have multiple cabs. So when you're purchasing your system or looking at the specs, you want to look and see how many throttles you can support and you do that based on your operator, on your operation. The other thing I'll point out is there's also different types of cabs. For example, you can see here the Pro cab there on the left. That one has full functionality, and you have the ability to control all 28 functions and speed control and everything, even do programming on the main, which we'll get to here in a little bit. But then down to the UT4 throttle there on the right, which is the DigiTrax version, which is a very limited cab. The problem with some of these is you only have access to some, 8 functions or in some cases 12 functions. And depending on your operation, you may want to modify that. For example, the Tsunami2 has a feature for fueling, function 17. So when you're running your diesel locomotive around the layout and you stop at the fueling rack, you may want to access that sound while you're fueling your locomotive. These UT4 throttles, unfortunately, are a little limiting, and so you either have to remap that down to a lower button using SoundTraxx function mapping, or you just have to sacrifice and don't do it, or you get the full-featured cab versions of the different throttles. So take that into advisement when you're going through and selecting your cabs for your layout. The next is the command station, and this is basically the brains of the system. What this does is this takes the command that you've pushed or the buttons that you've pushed on the throttle and turns it into a DCC signal. And then this is basically what controls it. Now, there's one command station per system or per layout. Basically, there's one that's going to create all the commands. Now, you can have repeaters or other units located around the layout that will repeat the signal or handle different districts and things like that, but basically all of the commands are being generated by one DCC system mounted on your layout somewhere. The next is the power station or the booster, and what this does is this takes that digital signal and amplifies it to track power, and then it sends it out on the track. So the power coming out of the command station may be low, but then once you add the booster to it, it puts it up to a level where the track power is being sent out and the decoder can accept and respond to the commands. Now, many times this is built in as part of the command station, and this will determine, again, what your needs are as far as picking a command station or picking a DCC system. For example, the DigiTrax Zephyr, we'll talk about that one, is the throttle, it's the command station, and the booster all built into one. Also, so is the NCE Power Cab. It has all 3 pieces built into one unit. Whereas there's other ones, for example, I know the CVP had the throttles, the command station, and then it had a separate track booster that would feed off and then send the power with the signal to the tracks. Now, different types of boosters may offer different types of scenarios. For example, short circuit protection will manage for that. So if there is a short, it'll shut down and protect the DCC system from that short circuit and also shut down track power so that it doesn't damage any of your equipment. There's also voltage regulation, so it tries to minimize any pulses or spikes of voltage that could be coming through. And then there's also auto reversing, and auto reversing is a little bit more needed because as you're running through the reverse loop there, as your locomotive travels through there, the track power may be in the wrong direction because it's a reversing loop. And so the auto reversing will detect that, and before the short circuit is detected, it will actually reverse the polarity to make sure that your locomotive can continue. So it gives you a lot better response than the old DC days where you had to get into the block, turn the track power off, change the polarity of that, change the reversing loop, and then start your train back up again to go back and through the reversing loops. There's a lot of cool things that the power station and the boosters can do. So again, check your system. Next up is our mobile decoder, and this is basically the brains of the locomotive, and this is what controls the locomotive. This receives the digital signal on the track and performs the task as you've told it to. And you want to set this between the track power and anything on the locomotive, such as lights or motor control, because we want the decoder to control that, because we want to tell the decoder how to behave. So we usually have that wired up that way. This sits and controls the lights, the motor, and in the SoundTraxx case is also the sound. Now, each decoder has a unique address or an identification, so the command station will be able to talk directly to that decoder only. So the address is usually a unique 2-digit or 4-digit address, and we'll talk about that here in just a moment. And again, all SoundTraxx manufactured decoders are considered mobile decoders, including our Tsunami2, Econami motor decoders, and even the sound car. So here's a few different examples of our Tsunami2 product line. You can see the TSU 1100 up there on the top left, our TSU 21P NEM to the top right, and then the TSU P&P down on the bottom. SoundTraxx has made different board formats to try to help make the installation a lot easier for you and fit into your model, but also be sure to check the specs of the decoders as well. For example, that TSU 1100 is only rated at 1 amp. So if your motor stalls at 1.2 amps, then you don't want to use that, and we'll get into motor stall current here in a little bit. Now the last type is accessory decoders. They're very similar to a mobile decoder, but they're more stationary, usually controlling things like turnouts. You can do signals, even control turntables and things like that. And the cool thing about being able to control turnouts is you can set, for example, on your throttle, you can set routes where you say to your DCC system, okay, I'm going to go down route 10 or whatever, and the DCC system will then send out a sequence of commands to all the accessory decoders to throw the turnouts appropriately, so then you can just run your train and you don't have to worry about stopping at every turnout along the way. So how this all works. So first thing, we take the cab and we adjust the cab settings. This is controlling speed or functions. We basically decide what we want to happen, and we use the throttle to tell the decoder what to do. So that signal is sent from the throttle down to the command station, and the command station receives the signal from the throttle and then creates a DCC signal based on what we want to do. That signal then is sent to the booster where it's amplified, and that amplification is then sent to the track as full track voltage. Now, one thing I did want to point out is everything up to the DCC signal going to the track is proprietary to the manufacturer. So if you're using a Digitrack system, for example, you cannot plug in an NCE throttle into their system because of that protocol is all a little bit different. Then once the DCC signal is sent to the rails, the decoder then picks it up, listens to the command, and performs the task as it's being told. Now this is where the decoder address comes into play, because if the command is sent to the address that your decoder is set to, then the decoder says, yes, that's me, and performs the task. If the DCC signal or the command is sent to a different address, your locomotive ignores that command and continues on doing whatever it was doing before, whether that's sitting still or running, blowing the whistle, whatever. So this is where knowing the address of the decoder is going to be very important. When we talk about the DCC signal, this is one thing that can be a little confusing or misunderstood. DCC is not AC power. It's actually what's called a dual wave or bipolar DC signal. DC is square wave, and as you can see here, you can see the square waves both above and below the zero line. Now this is also being sent at full voltage, and what the decoder does internally for power sources, it takes that negative pulse of power and inverts it. So you can see that in that square there, that if you invert that power and fold it along that zero line, you'll create a seamless power source, and so that way you've got your decoders using that as power, but it's interpreting the signal as it's being told. The signal is comprised of a series of ones and zeros, and as you can see there, the length of those pulses dictate whether it's a 1 or a 0 pulse. And so the DCC system will send that signal out, a series of ones and zeros interpreted as a command, and the decoder will then pick that up and perform the task. Now you get 8,000 bits per second basically through DCC signal, and multiple bits make up one data packet. So there's a whole series of commands that are being sent, and they're formatted in such a way, and this is where the standardization comes into play, is because every DCC system sends this signal out the same, so that way every DCC decoder can interpret it and perform the task. So let's look at the actual signal itself. Now don't let the drawing scare you guys. We're not going to need to decode this, but we're just going to give you a feeling of what the DCC track signal is. So the first off, we have the preamble. And the preamble is basically telling all of the decoders, hey everybody, listen up. And the preamble is a series of ones, and I forget the number, I think it's like 25 or 30 ones in a row, and the decoders then see that and go, okay, a new command is coming. So basically the preamble is, hey everybody, listen up. The next group is what's called the address byte, and it's basically telling the decoders what address this next command is intended for. So far the command says, hey everybody listen up, address 1000. And at that point, if the decoder is address 1000, it continues to listen. If the decoder is not set to address 1000, it goes back asleep. It ignores the rest of the command because this instruction packet is not intended for that decoder. So address 1000 listens up and says, okay, what do you got? And this is where the instruction byte comes in. And this is basically the command. This is telling the decoder to move forward, speed step 10, turn on F1, turn on F2, turn on F4, or whatever the case is. And then the last part is an error detection. And this is a sequence that tells the decoder that the information packet is complete. As soon as the decoder sees the error detection and the final part of the command and everything is registered, it then performs the tasks as it's told. Now the DCC signal, as I mentioned, is only sending a command, move forward, speed step 10, turn on F0, turn on F1, turn on F4, or whatever the case is. You didn't hear me say turn on your whistle, turn on your bell. That's up to the decoder to interpret. And so when the DCC signal comes through and says turn on F1, the decoder goes into its memory and says, okay, what am I supposed to do when I get the F1 command? And that's when it says, okay, I'm supposed to turn on the bell. So then the bell sound plays. And that's how the DCC system works. So when we're talking about, how to get your DCC system working with your decoder, well, the DCC system is simply sending a command telling it which functions to activate by number, function 0, function 1, function 2, and so on. And also move forward, speed step 10. Once the decoder gets that command, it then goes into its memory banks, and this is where you've set up the decoder to tell it how to behave. And it performs those tasks, and it performs them brilliantly once it's gotten the commands. So as you can see, over 200 data packets sent per second, and so you can get a pretty good instantaneous response out of your DCC system when you want to blow the whistle or ring the bell and press those buttons. So really quickly looking here, this is some look at the DCC signal using a oscilloscope. But the one thing I want to point out here is measuring track voltage using AC volts with a common household multimeter is going to get you close, but it's not actually an exact measurement. So what you want to do is you want to use an RMS voltmeter, something specifically designed for measuring this type of signal. You can also use an oscilloscope if you happen to have one or are proficient with it. But also our friends at Tony's makes a product called the ramp meter. And this is something that you can put onto the track, and it basically is an RMS voltmeter built in, and it'll turn it into a digital readout so you can get a more accurate measurement. So you really kind of want to look at this and use one of these tools to measure so you know exactly what your track voltage is. So now we're going to get into terminology. Now the one thing about DCC is there's a lot of terms that potentially can make it look more difficult than it can be. One of the issues with DCC in general was when it was being developed, they let the engineers name all the terms. And so to the engineers, a lot of these terms make sense. Things like programming and bits and bytes and stuff like that, rather than letting the marketing people come in and make the words a little more friendly. So hopefully in the next little bit here, we're going to talk about some of those and be able to make them feel a little bit more warm and fuzzy. The first one is configuration variables. What does that mean? Well, basically, a configuration variable allows you to vary the configuration or the setup of the decoder. So going back to our earlier command where F1 turns on the bell, we can use a configuration variable to adjust how that decoder behaves to an F1 command. So if we don't want the bell to respond, for example, we can change a configuration variable to tell the decoder that instead of a bell return sound, we want to play, I don't know, say the short horn sound or whatever, and this uses a configuration variable. Now in the decoder, these are used to adjust, as I mentioned, the performance. Now there's a handful of CVs that are industry standard, for example, and address CVs that determine what the decoder's internal address are. There's also ones that are called recommended practice, which means if you do this, we recommend you use this CV number. They're not necessarily standardized, but they're recommended. And so you'll see a lot of decoders. For example, CV29 is a great example. There's also manufacturer-specific CVs. And this is because with the different manufacturers innovating and doing things differently, for example, our FlexMap function mapping uses unique CV numbers. If we were to wait for everybody on all the different decoder manufacturers to agree on this, and then not only that are we sharing our technology, but also now we're having to wait for everybody to agree and decide on how they want to do it, nothing would ever get standardized. And so we have to push forward, and every other manufacturer will tell you basically the same type of thing. And so when you do that, we actually have our user's guide on our website that will go through and show you how to set the CVs and how to use them based on the way we've designed and programmed and set up the firmware in the decoder. Now again, because of that, not all decoders support all CVs. And so there are CV numbers that are in SoundTraxx products because we have a unique feature that we've designed and built to give you more fun that isn't available in some of our competitors' products. And so therefore, they don't have a CV to adjust it that way. The other thing, this is a rare instance, but not all CVs can be programmed by all DCC systems. And what I mean by this is if you have an older DCC system, sometimes you may be limited to 256 CVs, whereas with the Tsunami2, we have over 800 different CVs that you can program, numbered up to 512. And so if you don't have a system that can program up to 512, then you may be limited on what you can adjust with the decoder. And so this is one of the things, like I said, it's very rare, but check your system capabilities and find out. Now each CV is comprised of 8 bits. Now 8 bits is basically each an on-off switch. And each bit is unique and may perform a certain task and determine how the decoder behaves. For example, if we look at CV29, bit 0 has a purpose. It'll say whether we're moving forward or do we reverse the normal direction of travel. For example, the Southern Railway or the Norfolk Southern that ran long hood forward. We may want to wire the decoder in the same way but run long hood forward, and this is what this bit does in CV29. Bit 1 will determine whether you're in 14 speed step mode or 28 or 128 speed step mode. And so each bit may have a purpose. But if you look at this and you want a feature on, you will add the bit, put a 1 in there for the bit to be on and a 0 for the bit to be off. And each bit has a value. And if you look at the chart, the value doubles as it goes across. So bit 0 is worth 1. Bit 1 is worth a value of 2. Bit 2 is worth 4, 8, 16, 32, 64, and 128. And any number between 0 and 255 is a unique combination of these 8 numbers. And this is how the decoder performs the task. Now, some CVs, for example, volume are just a percentage. So 0 to 255 equals 0 to 100%. But the CV is still structured in the same way, even though you're seeing it as just a decimal number, 0 to 255. Now, we've got more on this in our user's guide, and if you do have any questions, you can contact us at support@soundtraxx.com, or we've got some videos on our YouTube channel that we can help out with this. But this is going to be fundamental because every single CV or configuration variable is structured the same way. Even different brand decoders, it's all structured exactly the same way. So get familiar with it. Now, making adjustments to the CVs, there's 2 basic ways for making CV adjustments. And this is where programming is kind of a misnomer because you're not actually programming the decoder. That's what our engineers do. But what you're doing is you're making adjustments or changing settings based on the programming our engineers have done. And this is one of the terms that, kind of is a little bit misnomer, but we're going to go with it anyway because it is somewhat of an industry standard. So when we talk about changing, there's 2 modes. You have service mode, which is use on the programming track, and then you have operations mode, which is on the fly or also known as programming on the main. So when we talk about the 2 different types, first of which is you have service mode or programming track programming. Now this particular method requires an isolated section of track. So when you have a small isolated piece of track, you're able to read a CV setting on a particular locomotive. The advantage to a programming track is that the locomotive address is not required. So if you have a decoder that you've either forgotten what the address is or didn't know what it was, let's say you picked it up secondhand from somebody, you have the ability now to put it on your programming track and interrogate the decoder and find out what the address is, or just flat out override it and put it on there and create a new address so now you know what the address is. Now, the way a decoder is read on the programming track is not the way you think it is. The way it's read is basically, let's go to elementary school when we played 20 questions with our friends. But now this decoder is playing a game of 256 questions with the DCC system. And the questions are, is the value of CV29 0? And when the decoder answers no, nothing happens. So the DCC system then moves on to the next question. Is the value of CV29 255? And the decoder doesn't do anything. So then it becomes, okay, is the value 1? Is it 2? Is it 3? And so forth. When the decoder finally answers yes to the question, it routes power through the decoder to create a surge in current. And that surge is detected on this isolated programming track as a yes answer. And so when the DCC system gets that yes answer, it then displays that last question in the window, CV29 equals 6, for example. This is why you have to have the small isolated programming track, is you cannot do that on the main line, because if somebody were to start moving a locomotive at the same time you're trying to read a decoder, then that surge in current or change in current draw could be interpreted as a false read. Now, the other downside or limitation on the service mode programming is you cannot test settings. So you will not hear the decoder start up and place volume, horn or bell or whatever, so you can't hear those changes in adjustments. So to do that, you can use what's called operations mode or programming on the main. Now, the biggest thing I do want to point out is programming on the main is no different than sending a function command like blowing the whistle or ringing the bell. The command basically, let's go back to the DCC signal. The 4 parts of the command is, hey everybody listen up, locomotive 1000, program CV29 to 6. And the decoder says, hey, I'm address 1000, and so then it changes CV29 internally to a value of 6. Every decoder that is set to address 1000 will respond. Every decoder that is not set to address 1000 ignores the rest of that command. And so by doing this, you can have the confidence to be able to then test your settings and hear those instant results. So when you're trying to do volume settings, for example, master volume CV128, you can do this on the main line and you'll be able to instantly hear that change as the decoder is being adjusted. Now, the biggest thing here, as I mentioned, you cannot read the CVs, and the biggest thing is you must know the decoder's address. If you do not know the decoder's address, or if it's not the one you think it is, again, it's ignoring the command. If your decoder is set to address 1001 and you're sending a command to address 1000, no matter how much we will that command to be taken, it's going to be ignored. So if it's not accepting it, pick it up, put it on your programming track, and try to read it and find out what's going on. So now function outputs. Now, one of the things you can do with the decoder is control things like lights. You can even turn on relays and other things that you want to do with the decoder. Basically, the function output is a response to the command. You tell the decoder when it gets a F5 command, for example, to turn on the ditch lights. Many of these are industry standard color coding wires, and so you can tell the decoder which wire to activate when it receives a particular DCC command. Now, the cool thing is that most of the tracked wire coming out of the decoders, the blue wire is the function common. It's rectified track voltage, so it's about 1.5 volts below. So when you're doing things like 12-volt lights, you can usually wire them directly. But if you're using LEDs and low voltage lights, you'll usually use resistors. Now, on the model, you can see there's a couple of different brilliances, and that's one of the great things the Tsunami2 allows you to do, is to wire up your LED with your standard resistor, and then you can adjust the brilliance so you can get things like number boards and step lights and truck lights dimmer than what would be a headlight or a ditch lights in this case. So next up, we talk about function control. This is kind of piggybacking on what we were talking about with outputs. With the decoder, you see the DCC command come in, and that DCC command, as we mentioned, can turn on different sounds, different lights, and things like that. When you see it written in your manuals and stuff like that, you'll see F0 through F28. The 0 key is this function, and all the way up to F28. When you're looking at your command stations, you'll want to identify how to access some of the higher functions, because there's not typically 28 function buttons on your cab. Usually you have to hit a pound or a shift or some sort of other button to access some of the higher features. So get yourself familiar with your DCC system so that you can access the higher functions as you go. So we've got, with the Tsunami2, we've got a lot of functionality built into there. We've talked about it briefly on our operation webinars that we've done already. And we also have a lot of videos on our YouTube channel that you can watch and see how some of those are enacted. So now when it comes to decoders, one of the biggest things is the motor control is done differently than a traditional power pack. When you adjust power on a power pack, you basically adjust track voltage. As you go slower, you have 1 volt, 2 volts, 3 volts, something along those lines. And as you increase the speed, the voltage goes up, motor turns faster, model moves faster. A decoder actually controls the motor a lot differently. It's using pulse width modulation, or PWM. And basically what it's doing is it's modulating or changing the width of a pulse based on the speed. So when your model is going 10% of the throttle, your decoder is sending full power to the motor for about 10% of the time, so about 1/10 of a second in a 1-second window. Now as you increase the speed, the duration of the on time becomes longer so that your motor turns faster. Until you get all the way up there where you see 100%, it's actually on 100% of that second, and then it'll be off for a millisecond and then come back on again. So basically power to the motor is being varied and changed as you go through the speed range. The biggest reason this is important is because stall current is a factor that is kind of overlooked by a lot of people. I hear things all the time about, well, I only tested in slipping. The reason this is important is when your motor have power sent to it, let's say when you go from 0 to speed step 1, that motor is sitting still because there's no power applied, and then you turn the command and you say speed step 1, and then you get that momentary pulse of full track voltage. Once that full track voltage gets there, you have a stall condition until the motor starts to turn. As the motor starts to turn, the efficiency of that motor and the current draw then drops significantly as your motor turns faster. So when we're measuring stall current, this is why we're measuring it. It's not because we as manufacturers think you're going to lock up your drivers or get stuck on a grade or anything like that. It's because every time you go from 0 to speed step 1, you recreate the stall condition. On our previous product, the TSU 750, our single biggest repair was the fast burn fuse that burned if you exceeded the 3/4 of an amp that the decoder was rated for. And that told us that people weren't measuring their stall current. And so because of that, we recommend that you actually do measure the stall current. And here's one method on way to do it. What you're measuring as stall current is what the motor is going to draw when the motor is receiving full voltage but stopped. And so by doing this, you can take a typical DC power pack set to the equivalent of your DCC track voltage, set it up, and in one of the leads you're going to have an ammeter set to DC amps. Now when that power is applied, that motor is going to be spinning, and so you're going to want to hold it still. To test the stall current, gently press on the model until the wheels come to a complete stop. At that point, you're going to see your ammeter actually go up significantly, and you're going to get a measurement. Usually with HO models are smaller, you're below 1 amp, but usually is not always. So again, measure your stall current. We had a customer that had an issue with a TSU 1100 decoder they were installing in a model, and this was a Kato HO diesel locomotive, which Kato actually has one of the better running diesels in HO scale. They run fantastic, but when we did a stall current test after he sent it to us with issues, we found that it actually stalled at 1.3 amps. And so because of that, we changed it out. We put a TSU 2200 in it. All the problems went away. We sent the model back. He's been running it ever since. We also have a video on our YouTube channel there that's linked, and you'll get that in the presentation later, or you can go to our YouTube channel and find it. But there's a couple of different ways you can measure stall current, and you'll actually see how they're similar and how you can get your measurement. So with that, we'll continue on. We got a couple more things to touch base with. So when we talk about speed steps, this is basically taking 0 to 100% throttle and dividing it up by 14 steps, 28 steps, or 128 steps. Now, I always recommend everybody operate in 128 speed step mode because your changes between speed steps are going to be a lot more refined. They're going to be smaller changes between each one. Whereas if you're in 14 or 28, those changes are very, very big, and you can get locomotive running pretty fast at what would be considered normally a slow speed, because you're basically jumping up, say from 28 to 128 speed step mode, you're jumping up almost 5 speed steps for every one that you'd be moving in 128 mode. So you really want to make sure that you're using the higher refined speed. The other thing here is 14 and 28 and 128, the different speed steps were developed as the command stations became better and more advanced. 14 was the original, and then 28 and 128 use a similar protocol. When you're setting CB29, you want to make sure you match, and the biggest reason is because of the location of the headlight command in that DCC packet. In 14 speed step mode, it's on, let's say it's at the very front, and in 128, it's towards the rear of that information packet. And so if your decoder is not matched to your command station, it's looking in the wrong place, and so you can get some erratic headlight command. Now, one thing to point out is with the Hyperdrive 2, the decoder, the Tsunami2, actually has 2048 internal speed steps, and that's interpretation between back EMF and momentums and other factors going in, so that the decoder gives you a very fine, refined speed throughout the entire speed range. And speaking of back EMF is using the off periods during those motor pulses that we talked about earlier to sense the motor speed. And so what that's doing is it says, okay, when the decoder is moving or set to, say, speed step 10, I'm supposed to expect a certain back EMF from the motor. Now let me pause for a second. Back EMF is, let me define how that works. When the power is being applied to the motor turns. When the flywheels and so forth are turning, of course, they create a momentum, and so it keeps that motor turning. When the power turns off to the motor, you have those windings spinning in the magnets, which then basically turn that motor into a momentary electrical generator because of the rotations of the motor and the flywheels. And that's what the decoder is sensing back from the motor, is that small millivolt power coming back from the motor. And that's how the decoder determines how fast or how many rotations the motor is turning, so that way it can try to help maintain speed at a steady rate. Back EMF decoders, it may be speed step 4 or 5 or sometimes even 10 or 12 before the motor would actually physically start to move due to either bind in the drive line or motor efficiency, things like that. And so that's where CB2, which is V-start, came into play, is so that way your motor would actually start turning at speed step 1. Well, with back EMF, the decoder will actually sense that the motor is not turning and will gradually increase speed until the motor starts to turn, so that way your V-start becomes unnecessary to really adjust or change. It also helps maintain a constant speed when you're going up or going down a grade, and it also improves your low speed control because it can sense if there's surging or something going on in the motor or in the drive line that the decoder can help overcome. Guys, thanks for participating and hanging in there, and we're going to look at some of the questions. If you have a question or need further explanation on something, send us a note and we'll try to cover it here.